Okay, good afternoon, everybody.
Good afternoon.
All right. I want to finish up today with our isothermal boxes, and then we'll move on. We'll do a little aside on gas molecular interactions next class. I think that'll be on Thursday. And then we'll move on to different conditions. We'll look at some other chemically relevant conditions besides the constant temperature. We'll look at constant pressure, constant volume, constant heat. They're all different conditions that we do chemistry in. We're going to find very useful tools that we'll use for the rest of the semester in this analysis. So already by fixing temperature, we've already come up with a useful one, which is temperature. I know that sounds kind of circular, but we've already seen some power, the power of temperature and how it tracks energy or available energy or heat or whatever work inside of a box of gas or a box of material, any material. I want to explore that I just want to kind of pull out as much as I can from that today. Essentially. So we're gonna what I want to do is I haven't really tied energy and isothermal conditions back to entropy. So we'll look at entropy again today. We'll revisit it from the perspective of our discussion on Thursday. And then we'll finish up with a very quick and easy derivation of Pivner, the ideal gas law. That will get us basically now to Gen count. In some sense, we build up the Gen count. And then what we're going to do on Thursday is break Pivner. Right? We're going to throw Pivner away. We're going to realize it's garbage except for very specific situations. We'll explore that next class. And also explain why it's bad. What's that?
Are you recording?
I am. Yes, I am. I set it to automatically record from here on out. So.
Oh, yeah.
So okay. So let's just go back to the big take home message from last class, which is the Boltzmann distribution. Which says that in a physical system, I like to say in a chemical system, because we're doing chemistry, equilibrated to a temperature T, the number of elements, or let's say, I don't want to use the word particles. You can think of it as number of molecules, number of atoms, and system with energy EI relative to those at a reference energy E naught. We can say the number of particles in state I or energy I divided by the number of particles in state 0. This is the number, N sub I is the number at E sub I is equal to E to the minus EI minus E0 divided by KBT. Right? And we can simplify that if we let delta E be EI minus E0, some energy difference, then we can just write E to the minus delta E over T. Okay. Right, so let me show you why this is an important equation in chemistry in general. You can make a lot of calculations with this. In fact, this is showing my nerdiness. I have a watch that has a circular slide rule on it. It's used for pilots. It's a way to do multiplication and division very quickly with a slide rule. It's a free calculator that no one uses anymore. But it's this two circular rings of numbers, and you can align them to do certain multiplication and division. And as a chemist, I always have my slide rule set to AT so that I can put in a temperature and I can figure out how much thermal energy, right? I can calculate RT. So really, it's a number I use every day in physical and chemistry. This basically how much energy is stored inside of this unit AT. Really, really important. And let me give you an example of this. Why this is important. This is one of my favorite examples from spectroscopy. And it's the problem of what's called the cyclohexane inversion. Everyone, I'm going to bring your trauma back by drawing some chairs. Right? But there's cyclohexane has two equivalent chair forms that interconvert between each other. Right? So if I label one of these H's with a color, maybe I'll just give it a star. Right? You have an equatorial and you have an axial one. I've marked one of them, right? And so there's an equilibrium between this structure where the starred H is pointing down and where the starred H is pointing up. Right? And people typically do this, studied this equilibrium by replacing the D with a deuterium, right, which is just hydrogen of the next neutron, heavy atom. Right. Right. And so here's an interesting question, right? What if I choose H prime, this special atom? What if I choose it to be fluorine? So I either have a fluorine equatorial or a fluorine axial. Special atom. Now let me pose this to you guys from organic chemistry. There's an orgo nerd in here. What's more stable, fluorine axial or fluorine equatorial? Or are they the same? I heard someone say something. I have an equatorial. Who said that? Why? Do you remember? Your argument is that if you make that a methyl group, equatorial is always stable, right? They always taught you that the axial you have strain when you have an methyl group pointing up rather away from the plane, because the H's on that methyl group touch the other hydrogens that are pointing on the ring. So it generally prefers equatorial. It turns out in fluorine it's the opposite. Very, very strange effect, but in fluorine it's the opposite. And what we find is that for fluorine, the relative energy of this one, we'll just say is 0 kilojoules per mole. And let me just clean this up. So I'll just make this an F instead, just so I can save some space. And when you do calculations, you find that the relative energy of the equatorial, contrary to what you would think, the argument is exactly correct that you'd think it'd be equatorial, but it's axial in the case of fluorine, is that this is destabilized by about 2.5 kilojoules per mole. Okay. So the question then comes to the question is imagine you have an NMR sample. You have a sample in your NMR tube that you put in your NMR at 300 Kelvin. What's the distribution of these two? How much of this do you have relative to this? Right. Well, you could calculate an equilibrium constant because you know the energy difference, but you don't even need to do that here because we're equilibrated to a specific temperature. The molecule can be in two energy states in this perspective. It can be in its low energy axial state or its high energy equatorial state. And so all we have to do is this system is equilibrated to some temperature. All we have to do is consider the ratio of molecules in the excited state, the ratios to the molecules in the ground state. This is our excited state, this is our ground state. So all I have to do is calculate E to the minus 2.5 kilojoules per mole divided by RT. wherever the temperature is. So the number of axial, so the number of equatorial, the number axial can be determined directly from this value, e to the minus delta E. And here I'm just going to use RT because we're doing things in moles. So that's going to be e to the minus 2,500 joules per mole, right? Because it's 2.5. Divided by 8.3145. That's the gas constant. Joules times moles times Kelvin. And our temperature, we'll just say, is 300 Kelvin. That's a really easy calculation to do. Just a quick exponent. And the value I get for that is 0.36. So it says that for roughly every 3 axial molecules, roughly, you get 1 equatorial. 36.64%. Right? So at 300 Kelvin, I already know the answer to this question, right? But this is 36%, and this is 64%. Right? What happens as I cool or warm? Well, the exponent gets smaller as I cool, right? Which would make this number, right? You have a smaller exponent if I drop it from 300 to 200 Kelvin. The exponent is smaller, meaning that the denominator is smaller, meaning that the exponent is getting bigger because you're taking a number and dividing by a smaller number. So this is getting bigger. You're taking e to the minus big number. That means it's getting smaller and smaller, the result. Right? So as temperature goes down, the amount of axial you have increases. That is enough. And then as the temperature decreases, you get more equatorial. Okay? And it travels, right? It scales as this exponential function. Okay, so by doubling the temperature, you don't double the concentration, right? Because it doesn't go linear, it goes exponential or logarithmic. By doubling the temperature, you only increase the abundance of the excited one by log of 2. Right? 1.2 about 60%, not 100%. So this is a logarithmic scale. Energy or abundances are logarithmic, not linear. Right? And I can show you that really, really simply. In temperature, not linear. Right? Temperature is a logarithmic scale, not a linear scale. And the reason is very clear. Is once you look at it in a specific way. Is that we could say that Ni over N0, right? This is basically the relative abundance of I, right? Whatever element I is, state I. Right? And that's equal to e to the minus delta E over KT. Right? If I take logs of both sides, I have the log of the relative abundance is equal to the log. All right, I'm going to write Ln, natural log, of e to the minus delta E over KT. What's the log of E? By exponent rules, this is minus delta E over KT times the log of E. And what is the log of E, guys? What exponent do you need to raise E to get E?
1.
Yeah, exactly. So this is just 1. And so what it says is that the log of the relative abundance is equal to minus delta E over KB times 1 over T. Right? So what this means is that the log and the temperature are inversely related to each other. Right? So it's a logarithmic scale, non-linear scale. Right? You have to take logs of abundances in order to get linear relationship with temperature. So it's not, so temperature is kind of a funky scale. It doesn't work like meters or mass, right? If you double the mass, you get double the material. If you double the volume, you get double the volume, right? But here, if I double the temperature, I don't get double the abundance. Right? Because temperature relates to our observables in a logarithmic way, not a linear way. Okay? So T is kind of a weird number for that reason. Right? And some right, what this means is that if I take my temperature from 200 to 400 Kelvin, as I said, you don't get twice as much stuff. You get some logarithmic stuff. Right? So it doesn't scale linearly. And so temperatures are kind of weird. You can't add two temperatures together necessarily. Right? Like you put two masses. There's not a conservation of temperature. Temperature is something that measures an average, but as we can see, it measures an average of a logarithmic quantity, not a linear. Temperature is kind of a funky number. But this logarithmic ability is tied in directly into the nature of temperature. Temperature is logarithmic, measuring a logarithmic value because what it measures, what it represents, temperature represents, is also represented by logarithms. Energy is a logarithmic quantity. And I want to show you that today. By considering now with this approach in our isothermal box, how does the entropy of our box change as we fluctuate the temperature? So what we have so far is this, right? We've looked at our box now as a random distribution of energies, right? We have all these particles moving around randomly, and they have a random distribution of energies, and the probability of finding a particle at a given energy is satisfied by the Boltzmann distribution, e to the minus delta U. Right? So what we're doing is we're not picking things out of a box that are normally distributed like a bell curve. We're picking it out of a box that's weighted with a distribution of probability that is exponentially decreasing instead of bell curve. Okay, so the statistics are going to be different than you would expect because the shape of the distribution is different. So what I want to think about is when I change the temperature of my box, should warm the bath up or cool it down, how does the entropy of the box change? And so what we're going to look at is how the statistics of the energy change, right? As the box heats up, your molecules will more readily exist in random energy states that are higher in energy. The hotter it is, the more hot stuff you have. Right? So that as you heat or cool your box or your material, that energy distribution is going to change. It's going to shift to the right or shift to the left as you heat or cool. And what I want to look at is that how does the entropy get affected as this probability changes, as we heat and cool. So how can I connect entropy to probability? We're going to have a really, really nice relationship. So how does P get us to S through statistics? Right? If you've already worked on the first set of problems in the problem set, I think it's 1.4, you have this question where you have to calculate U from this Q number. If you haven't seen this yet, this is going to be something new to you, but it's something you're going to play around with. Problem set. I'm going to bring that concept up today. And so what I want to define, let's define a few things just so we're all on the same page. Okay, so define the probability, this function rho of EJ, to be the probability of observing EJ in an object inside a box at temp T. And this probability, we know, has this addition, this factor of e to the minus EJ over KT. Right? I've used K here as K sub B, Boltzmann's constant. I'm just going to write it as K. Anytime you see K times T, think Boltzmann's constant. I don't think there's any other K's multiplied by T's in this class that aren't Boltzmann's constant. But remember that this number gives you a relative abundance relative to a standard. Okay, so it's not an absolute probability. It tells you the probability relative to something. Well, what I want to have a function here is the absolute probability that when I pick an object out, it's at energy EJ. And so I need a coefficient here on the outside to account for, in some sense, all of the possibilities of the box, right? I need to know what are all the possible things I can pull out of the box. And then it's very easy for me to calculate which fraction of those is just that one energy. So I need to divide this by a special number in order to account for this. And this has a special name, we give it called Q. And this is what's called the partition function. We're not going to really talk about these, but you see them in the homework. And what this specifies in some sense is it's a count of all accessible, let me be very careful with this wording, energetically accessible states. Right? Remember that I said as the box gets hotter, the molecules and the atoms, they can sit or they can exist in higher energy configuration. They might be moving around faster, they might be wiggling around. The hotter it gets, the hotter they move. And so Q tells you as a function of temperature, what are the total number of possibilities? Okay, it's a count, a total count. And so what this is saying is what are the fraction of molecules out of all the possible arrangements that are exactly the J energy? How many out of all the possible energies are exactly E sub J? Right, so that's our probability. The Q is something that you can calculate. A Q is a system-specific number. Right, so it depends on what you're looking at. The Q depends on the box conditions and material. Right, but thankfully for an ideal gas, it has a nice closed form expression. And it's the one that I give you guys in the homework. Q is a function of temperature. Two pi times the mass of the particle, kBt, over this constant h squared to the 3/2 power times the volume. Sorry, I need two factors of n there. All right, so I could plug in a temperature, plug in the number of particles I have in the box, it's n. These are just numbers. This is the mass, this is constant, this is the volume of the box. And what this tells me roughly is how many possible configurations the system has at a given temperature. And you can see that it gets bigger with T, right? As T goes up, it's the only variable in this at constant volume. It's the only variable. And so as T increases, the number of possible arrangements increases. So I don't know configurations. And Q just exponentially increases, right? So if I were to look at this as a function of T and plot it as Q, it's just an exponential function. No, it's not. It's a linear function. Sorry, it's a linear function. Okay. Okay, so Q just measures kind of, right, how many, I want to calculate how many particles have energy E sub J, And I need to figure that fraction out with the total number of part, basically the total number of energies I have, which is what it tells me. So it kind of just normalizes my equation. Okay, so Boltzmann takes this approximation and he starts to think about the concept of entropy. And he comes up with an equation that we're not going to derive, but I want to talk to you today a little bit about what this equation means and what is it telling us about entropy. And I'm going to write it down and you're going to be like, this equation is awful.
A hot new equation enters the villa.
Yes, but it's one that we're not going to use for long. We're just going to use it as a jumping board. What Boltzmann derives, and this is what made Boltzmann famous, is this approach to entropy, is he writes that entropy S is equal to minus KB. Right, so you got this constant on the outside. And then what he's going to do is he's going to sum over all the states, or all the possible energies from 0 all the way up to infinity. All right, so there's going to be a summation of all the possible energy states from I equals 0 to infinity. We're going to sum over all the possible arrangements. He's going to sum all the probabilities. Okay. So the entropy has something to do with the probability of finding your system in a given energy, given motion. And it turns out that it's times, he has to add an additional term, the logarithm of the probability. Okay, so he defines that the entropy is the probability times the log of the problem. It seems to be an I.
Okay.
Sorry, it's an I apologize. Of the I. Right, and I know this equation seems odd, right? It's not really clear why it has this structure, why the entropy is, I mean, it maybe makes sense that the entropy, right? The higher the entropy, the more motion the system has. So obviously, the higher the entropy, the higher the probability is to find a particle exhibiting some motion. So that makes sense, but why the log, right? And it turns out this just comes from the statistic, the calculus, that this comes out. But what I'm interested in is, what does the change in entropy look like? What if I take this equation and I adjust the temperature very slightly? How does the entropy change? What is S? What in some sense, what's the derivative of S with respect to T, with respect to these probabilities? And when you do this, you get a really nice equation that tells you exactly statistically what entropy actually represents. So bear with me with this math a little bit. What I want to do is I want to take a derivative of this. I want to vary entropy and I want to adjust it with respect to temperature. And I want to see how the probabilities change. All right, so let's do a little bit of math. So we have a KB here. Sum over I to 0 to infinity. And what I can do now is I can plug in my probability equation into my expression
Q
here.
also?
What's that?
Are you going to plug in Q also?
Yes, I'm going to plug in Q.
Oh.
Yes, but no, not the whole thing. No,
Oh,
I'm going to leave
okay.
Q. I'm going to leave Q by itself.
Okay.
I'm just writing Q down here because this is what it looks like for natural gas. Q is just going to be a number.
Okay.
It's a temperature dependent number, but it's just a number.
Gotcha.
We don't really have to worry about how Q varies at the moment. Right, I'm not going to type. Yeah, that would be nasty. Not that. We're not going to be that precise. All right, so I can go ahead and put that 1 over Q e to the minus E sub I over KT. And then I have the log of it. And so and I can clean that log up. It's log of Q minus EI over KT. Okay, that's what the log of Q. rows. And the Q disappears, right? You can separate this. This is Q to the -1. And then you lose the E. Okay. Okay, I can do some arrangements of this equation. And I get that this is equal to the sum from I equals 0 to infinity times a negative sign. There's a negative sign on the outside of AB log Q plus EJ, EI over T times E to the minus EI over T. Okay, I just did some distribution of all the terms and simplified some things out. Okay, I'm not really doing anything crazy. Okay, we already see that the entropy splits out into two terms. We already see that there's some entropy that we could say is the entropy of the entire system. Right, log of Q represents all of the possible combinations, right? So the entropy has something to do, in some sense, with the amount of information that the system stores. If you think about each motion the atoms or the molecules can have as a piece of information, the entropy is proportional to that amount of information, which is Q. Right? So in some sense, it stores the energy of the information of the entire system. And so how do I define this exactly? Right, so this is the entropic content of the entire system. Right? And that's just a function of temperature. As the system gets hotter, there's more motions and more energy that it can express, and therefore, in some sense, it contains more information. And entropy, as you'll find out, it has something to do with the complexity of the information. If you, for instance, think about a piece of text, let's say thousands of words long, right? And you can actually calculate. So you can calculate the entropy of the text. If your text is very ordered, meaning that you have complete sentences and complete words and everything is organized nicely, your system has very low entropy. But if you have like scrambled text, cipher text, it generally has very high entropy. And in fact, this is how cryptography typically works. One of the ways that people hack cryptography or cryptographic schemes is to use entropy by rearranging things and minimizing or maximizing the entropy of the changes. And so the idea here is that this is in some sense the entropy content of the entire page or the entire document. And as the document gets longer, obviously the entropy increases because there's more and more information. And then this term here is an individual term that contributes from each of the elements themselves. Right, so this is the entropic content of a single piece of information or a single motion of system. Right, so there's kind of like an entropy component that represents the entire system. And then there's a temperature weighted component, depending on the temperature. If the temperature is really small, then this weights heavily the states that have low energy. And if your temperature is really high, this weights the states that are very high energy heavily towards it. Okay, so we have two, right? But again, this doesn't really tell me a lot. It just tells me that I can represent two individual components of the entropy, but they still don't have a lot of physical information for me. I can calculate them out. So what I'm going to do is I'm going to take this S equation, and then I'm going to vary. I'm going to go from S, and I'm just going to pump in a little more entropy, right, to ds, by maybe increasing the temperature or putting some heat into the system. So I'm going to now vary S S plus ds. And when we do the analysis, when I do the algebra, I'm just going to kind of simplify it. I'm not going to go through all the calculus because it's just to describe it. You find that the change in S is equal to minus KB times the sum over all the states. And we got kind of a big nasty equation, but we'll simplify it. It's times the change in the probability of the given energy E sub I. That's the variance, how the probability changes as S changes. So this is the variation in the probability. And then there's an additional term, which is the log term. And E of E sub j times the derivative P E sub j. So this is the variation in the probability. Right?
EI, you mean?
Yeah, EI, thank you. I'm sorry. I like using J a lot, and you can see that I'm making mistakes. All right, but we can make some simplifications here. And this is a very, very subtle argument. This first term right here, right? This first term, each of these little d's of P are how each of the probabilities are changing for each of the energies. So maybe you have, let's say you have 4 energies, right? Just 4. 1, 2, 3, 4. E1, E2, E3, E4. And imagine the probability of E4 goes up. What has to happen to E3, E2, and E1's probabilities? If one goes up, the other must what?
Go up, go down.
No, go down,
Oh,
right? Because
right,
probability
down.
is conserved. Right? If you have more chance, if you roll a dice and it's loaded, and you have 60% chance of getting a okay, I'm just careful with the math, right? So if the probability of having rain increases, then the probability of it being dry decreases, right? So
Yeah.
probabilities are conserved. Right. So what I'm doing here is I'm summing over all the changes of all the probabilities. Some are going up or some are going down. But the total probability is 1.
Yeah.
So the changes, the sum of all the changes goes to 0, right? Because for every one that goes up, something also must come down. Probability is conserved. So this term right here goes to 0 because probability is conserved. Well, we can get rid of that term. And so all I'm left with now is this logarithmic term, the strange log term, times the minus KB of the sum. And what I can do now is then sub in my equation for the probability. Right, we can sub in our Boltzmann distribution here. And what we find is that ds after we do a bunch of math, all right, I'm just going to, and then we do a bunch of simplification. I'm not going to do the simplification just to save time. But I want to get to the final answer, which is this, is that the change in entropy is equal to 1 over T times the sum over all the possible energies of the energy times the probability, the change in the probability of that energy being observed. Now let's break this equation down a little bit. I forgot an error. Let me clean this up. I'll call this D, and then I'll put this in brackets. All right, so the change in entropy again has some information about the temperature. It has some information about the available energies that you can choose. But the important thing is that the the way entropy changes, the real change that's affecting the entropy is that the probabilities of each energy is changing. So entropy has something to do with a balance of energy times the probability. Right? In some sense, this is, if you think about this, this is how the probability of finding a given energy in your system is changing, and it's divided by the temperature. So what are the units here? The units here are joules. This is a probability, has no units. Joules divided by temperature, which is Kelvin, joules per Kelvin. All right, and the entropy units are joules per Kelvin. And so our units work here. So let's look at this graphically and see what's happening. Right? What does this tell us about entropy? And I like to think about this graphically. So again, think about making a box of gas or liquid, it doesn't matter, some material, and asking each atom, what's your energy? Pluck one out, take a snapshot, ask it for its energy. And what you're going to plot is the number of answers versus the energy, right? The probability of getting that answer. And what we found, of course, is that's the Boltzmann distribution, e to the minus. So at some temperature, we could say that the distribution looks something like this. This is delta E, and this is probability of observing delta E. I'll just write E instead. And let me just mark a couple of points on this curve. Maybe we check energies at this one, E sub I. Maybe we check ones at E sub J. Maybe we check something at E sub K. And just to be safe, we check at E sub K plus 1. Right? And what this says is that out of all the molecules, right, out of all my checks, the probability I'm going to get a molecule in energy E sub I is, that's the probability. And let me clean this clip up because it made a straight line and I didn't want it. Let me clean up this. There we go. So this is the probability of finding a particle in the system. Right? And again, you can think about these as like isomers, right? Imagine cyclohexane had 5 different arrangements or 4 different ways to arrange the atoms. This is the probability of finding one, or the relative abundance of one. This is the relative abundance of the second one, the third one, and so on. Different ways to do it. So what happens now as the temperature increases, right? So now let's jiggle the temperature of our box. Warm it up or cool it off. So I'm going to warm it up. Right? What's going to happen? Well, remember that our probability distribution is 1 over KT. Right? So as T gets larger, the exponential becomes less exponential. It decays more slowly. So what's going to happen now at a hotter temperature is that we're going to have the same curve, but it's just going to decay much more slowly towards 0. So if I heat up, I'm going to get a curve that maybe looks like this instead. Right, this is at T equals T hot. Right. And this one is at T equals T cold. Okay. Excuse me. So so what happens to my system probabilistically? Well, now I have a higher probability of finding all of these states than I did before, because now there's more energy, it's more biased in some sense towards the high energy wing. And so the probabilities have all increased. So I can draw little lines here to connect. This one is increased by this much, this one this much, this one by this much, this one by this much. Right? And so these little green lines here, right, this is how the probability of that energy has changed. So this distance is just d of p of rho at E sub I. Right? It's just the change of the probability at that point. Right? That's this right here. Okay. So when S changes, part of the entropy calculation is measuring how much Y increase do we get for each energy. Okay, but it's multiplied by the energy of itself, E sub I. And I'm going to sum from E sub I to E sub j and all those different numbers. And so when I do this calculation, and I calculate the difference of the entropy at this point to this point, right? So I have an entropy for each. So I have S hot, right? S for this one is S hot. And this one down here has an entropy S equals S cold. What is ds? Well, ds is the product of the energy times the change of that probability when you heat it up from entropy 1 to entropy state 1 to state 2. And so when you do that math and you work it out, you find that the entropy, the change in entropy is just this area under the curve. So this area under the curve is delta S, which is equal to 1 over t times the integral from 0 to infinity of Ej times d of p of j. And we sum all of them. Let me clean it up. I'm sorry, I have a little too much here. Delta S, and we sum over all the different states. And so each one of these little regions of integration we've done between individual points are just integrals of that area. And that's just a change in the entropy. So what entropy is, from the point of view of Boltzmann, is that first of all, it has some energy content. But the important thing about entropy, the thing that ultimately determines how entropy changes, is how does that energy get distributed amongst all the different possible motions or different types of arrangement. Each of these motions have a different energy, and the entropy measures how much that varies, right? So you can imagine, theoretically, there could be some system where you have some energy in it, but when you change the state of the system, the probabilities don't change. Right? Then the entropy doesn't change. So any entropy change indicates, by definition, that there's a change in probability of the different motions that are being seen. So a change in entropy is a change in the statistical distribution of energies, motions, or arrangements of the molecules or atoms in the box. Okay. And it's really, really easy. Now, remember when I said that when we first introduced entropy, I said the entropy is linear and it's monotonically increasing, meaning that as put more energy in, the entropy goes up, right? And it should be clear now why that is. Because what happens is as you start to heat the system, the probability distribution rises in probability. And the change in entropy is the area between the two curves, between the initial and the final state. So if, as you heat, this second, the curve at higher, the final temperature is increasing. So when you take that integral, it's positive. The change in entropy is positive. But if you cool, right, what's this curve going to do? It's going to go below this one. And now your integral is a negative difference of two functions, and therefore the integral will be negative. and the entropy decreases. Right, so the only reason why entropy is monotonically increasing the temperature and always increases of energy is exactly this, right? Because these curves are moving monotonically with respect to each other as well. And entropy only measures how the area under the curve changes as you go from one state to another, one condition to another. Right? So this is why when people say that entropy is the measurement of disorder, you can understand exactly why people say that, right? As the entropy increases, we're increasing the probability of finding more states, finding our particles in more excited states, more excited motions. There's more of a chaotic morass of stuff going on. It's more disorderly, and therefore the entropy is higher. And as you slow things down and lock them into place, can't vibrate as much, they can't oscillate as much, they can't move around as much, the entropy drops, and therefore the temperature also drops. Okay? So this turns out to be really, really powerful, because not only is this applicable to science like chemistry and physics and engineering, but people use this idea in, as I said, in cryptography as well, and other types of language analysis like that. You can measure an entropy of anything. Information entropy has the same rules. In fact, there's a really, really cool paper. I don't have all the tools for it yet, but looking at the entropy changes of what do you call it, gridlock on I-95. You know, sometimes you're driving on I-95 and you're in traffic for like 10 minutes for no reason whatsoever, and you're like, why the hell are we locked in traffic? There's nothing going on. There's no wreck or nothing like that. It turns out that if you analyze this from a thermodynamic point of view, that gridlock is a change in the entropy of the system that is actually associated with a phase transition as well. And we'll look at that. So entropy is a universal concept, and it just basically measures the information, or in this case, the heat content of your material. And all heat is just motion. The more motions there are, the more disordered, the higher the entropy. Okay. And I just wanted to look just really quickly. Remember that we said that Joule said that the change in entropy is 1 over temperature times the change in heat, right? So we get the exact same expression. We have temperature is inversely proportional, entropy is inversely proportional to temperature. And then all the change in heat is just a measurement of how you're injecting new heat, new energy into the probabilities. This is how you're injecting energy into the statistics. And so it's dependent on how the probabilities change. Okay. So that was just a little bit of theory. And what I want to close out with is another application of this idea. Of the idea of having this Q, this partition function that measures all the possible arrangements of the system. What else can we learn from these tools? Turns out you can learn everything from doing this analysis. One of the powerful things about Boltzmann. So we've been learning Gibbs, and we'll learn a lot about Gibbs and Joule. We'll use a lot of their tools. Boltzmann used statistics to rederive, in some sense, independently from Joule and Gibbs, a statistical approach. We call it statistical mechanics. This is very, very basic statistical mechanics, where we use statistics to determine things about energy. And it turns out the statistical mechanics and Gibbsian and Julian thermodynamics, they tell you the same thing, but from two different perspectives. Right? So in Joule's case, he thinks about heat for entropy, right? But Boltzmann thinks about changes in probability. And they're equal. They're the same thing. You're just looking at them from two different perspectives. Okay. So I want to use the statistical approach one more time. And we've got 20 minutes, great. Enough time to drive this. So one really, really simple derivation. I want to use statistical information to get us to show you that Pivnert falls out of the statistical approach. And that will, in some sense, loop everything back together. Started in some sense with Pivnert as an assumption. And we've worked out all this box bullshit. And somehow I'm going to convince you that everything comes back together in one big loop.
Wait, so now we're gonna break Pivner?
Well, we will next class.
Okay, not yet.
I'm gonna bring up Pivner, and what we're gonna do next class is we're gonna look at how experimentally accurate Pivner is as a model. Right, we're gonna evaluate Pivner as a model next class, and we're gonna find that it doesn't work very well.
Yeah, that one review you showed in the first class talking about this guy loves his boxes of particles. He's not lying.
No, not at all.
Not lying.
Not lying about that. Okay, so here's a really nice
Yeah.
Here's a really nice formula. When you have a statistical distribution, e to the minus LP over KT. Once you have the distribution, say it was a bell curve, for instance, or a functional bell curve, you can calculate any statistic you want about it. Right. So what I want to calculate today is for an ideal gas. I want to calculate the average energy. What is the average energy? So if you have a gas at room temperature, how much energy does it have on it? Good question. For any system, and this is true of statistics, any sample, any system or sample with a probability distribution P of X, right? Like the Boltzmann distribution or a bell curve. The average value of a variable let's call it big X, is defined by X hat. When I write a hat, this means average or mean. Sometimes I will write it like this.
Is that big X?
Yeah, big X with a bar over it. And sometimes I'll write it like this in squiggly brackets or curvy or angular brackets. These mean an average or a mean. Is equal to the integral from 0 to infinity of the variable times the probability distribution evaluated for that variable dx. Okay, so in order to measure a variable.
Wait, I'm sorry. So it's big X times P little x D
No,
big
these are
X.
big.
Oh, they're all big X's.
They're all big X. So in order to measure the variable x, we have a distribution that measures x. Measure x. X here is E, right? Energy. So we have an energy and distribution, the Boltzmann distribution, P of E. In order to measure the average energy, I'll just write it down. We just need to plug in E times P of E. So just really example, for the average value of the energy at some temperature T is equal to the integral from 0 to infinity of E times P of E, dE, which is, I'll just plug it in, 0 to infinity E times E, oh, sorry, I forgot the Q, times 1 over Q, E to the minus E over KT dE, right? So all I have to do is take my integral or my distribution and just multiply it by energy and then integrate the whole thing with respect to E, and that gives me an average value. This is a true equation. All right, so but the problem here is I don't know what Q is. So let's do it for an ideal gas, right? We just wrote that down on the last slide. So let's apply an ideal gas. Right, and let's calculate the average energy of an ideal gas. Right, you guys approach this problem in the homework a slightly different way, right? Using derivatives instead of integrals, but you get the same answer. Right, and so this is going to be 1 over v to the n h squared 2 pi m kbt to the 3/2 n power times the integral of e times e to the minus e over kt dE. Right. This is kind of a long and complicated equation that we have to evaluate. We have e to the minus delta e, so we have to do this by parts. This is integration by parts. We're not going to do that. I'll never make you guys do any integrations by parts in this class. But we integrate this by parts. You guys learn that in Calc 2 or Calc 3?
2.
2? That's what I thought, yeah. So you do this by integration by parts. And the answer is just beautifully simple. What you find is that the average value of E, all this crap disappears. And you end up leaving with that delta E is equal to 3/2 kBT.
Is that the answer for the homework too?
Yeah, it is. That's the homework. So that's a good check. All right. You derive it a completely different way from this. Okay. So the derivation is the more interesting. It's really just a partial derivative practice problem, but that's the answer you should get 3/2 kBT. This is a beautiful equation, right? All it says is that, right, for an ideal gas, if you know the temperature, remember temperature is Kelvin, kB times T is joules. So this converts temperature into energy, and it's just 3/2 that. And it's amazingly how simple that is. Let's look at this equation very briefly. What is it telling me? Right? Why is it 3/2? Why is this? I mean, it's a nice number, but there must be like some sort of like reason why it's 3/2 in particular. It must not just be coincident. And here's the reason. Here's the reason why. All right, let me do it on another page. Just that simple. Cool. Why 3/2? Well, I mean, imagine now we have this box. I'm not going to draw it really complicated. We just have a box in here, and inside of there is an ideal gas particle. All right, so here's one of our particles. All right, and remember an ideal gas, the only type of energy we have is kinetic. No interactions. Right? So this particle is moving with kinetic energy in 3 different directions, right? It could be moving in the x direction, it could be moving in the y direction, and it could be moving in the z direction, right? So we could say that the energy of this particle, the kinetic energy of this particle, is equal to 1/2 m times the velocity along the x direction squared. All right, now I'll write the velocity. So the velocity is x. This is the velocity y. So the velocity z, the velocity y. Right. So it's moving in some direction. Plus the energy of it moving in the y direction. Plus the energy of it moving in the z direction. Right. So what I can do is, right, I can separate its motion in the x direction from all the others, right? And I can do that because, in some sense, moving along x doesn't affect y, right? That should be pretty obvious. Then I could split it into 3. Oh, so it's a vector after all. It's got 3 individual components. So it has 3 individual components. There's an energy along for the x motion, energy for the y, and energy for the z. Right, so I can also say that the kinetic energy is equal to some energy along the x direction plus some energy along the y direction, plus some energy along the z direction. Right? And the total energy is the sum of the three, right? So energy in a 3D box, or let me say kinetic energy, to be specific, in a 3D box is like the sum of motion along three individual lines. Right? It can move with some energy along the x line, it can move with some energy along the y line, and some energy along the z line, but they're all separate. So this energy problem isn't really three-dimensional, but rather it's three one-dimensional problems added up. I can treat the energy separately, and it doesn't really matter whether I go x, y, or z, right? They're all the same. So the energy along z is the same as the y as is along x. They're all the same. Right? So what I can do is, instead of thinking about three-dimensional motion, I can think about this moving on three different lines simultaneously. So I can separate each energy contribution separately and think about the probability along each of the three lines. And what you find is that when you take this idea and you calculate the average energy along one of the directions, so just along x, and it's equal to just along y, which is equal to just along z, exactly the same math I did before, but now I'm integrating over one dimension instead of three. It comes out to 1/2 kBt. And this is a super important point, is that each motion in your sample, and we'll talk about the different types of motions things can have, contributes exactly 1/2 kT energy to the heat of the system. Right? And now you understand, maybe you understand why now it's 3/2. The total energy of the box, which is moving along all three directions, is the sum of these three. You move along x, y, and z. So you have 1/2 plus 1/2 plus 1/2, which is 3/2. So you have 3/2 kT. Right. So this number right here is super important, this idea of kT. The idea here is that kT, which has units energy, is what we call the average thermal energy of the system. So in some sense, kT is the heat available from a bath to do useful work, say chemical work or physical work. So if you heat your bath up to 300 Kelvin, the amount of energy your system has from that bath to use is on the order of kT. Okay? That's how much energy temperature gives you, right? So the important thing here is that K, this number K, converts between temperature and energy. K tells you how much energy you pump into a molecule as you heat it up 1 degree. Or RT, for instance, is how much energy you give to a mole of atoms if you heat them up by 1. Right? The average energy of the system. And so if we want to think about, for instance, a reaction that needs a little bit of energy to get started, a little kick, you want your heat to give it that kick. But let's say, for instance, your energy is RT, but that kick needs to be 2 times RT, right? And so what's going to happen is not every molecule is going to have enough energy to get that kick. So not everything is going to react all at once. Right? And what we're going to find is that ratio of the number of molecules with a certain amount of energy compared to some barriers, some critical amount of energy to do a reaction. Imagine your energy is here and the barrier is up here. You got to get enough energy to go over it. Only a small number of high energy molecules are going to have enough energy to get over that barrier. And what we're going to find is that ratio, basically the ratio of atoms that have average energy below the barrier to the height of the barrier, the distance between the barrier and KT, that ultimately determines the kinetics of the reaction. If you have most of your molecules have enough energy to get over that barrier and to react, then the reaction is going to be very rapid. But if your barrier height for your reaction is very, very large compared to KT, the reaction is going to be very slow. So that's a little bit ahead of kinetics here. We have this energy balance. Heat provides a certain amount, a fixed amount of energy, and that's all we have to use. That's all we have to use, unless we provide additional energy from something else. Okay, so I'm running out of time, so I can't. The derivation from Pivner to here is not hard. Requires another calculation. But what I want to show you again is that we have, in some sense here, if I multiply this by Avogadro's number, I have nRT. N times Kb is R. So we already have, in some sense, the right-hand side of Pivner here. So let's just look at Pivner really quickly from this perspective. So we can already tell you, we can already express this, think about this more carefully on the right-hand side, right? This is some sort of heat content, right? The entropic content of the material. Right, so what nRT is, in some sense, is the energy provided from a bath at some temperature. Right, like the air. Okay, so you have this gas. Imagine I have this little cylinder of gas. Okay, and inside of it, I have a piston. Okay, and I put some gas in here. Like that. Okay, and I feed in nRT. Right, I feed it in, I have it in a bath, and I'm kicking in. Right, I'm kicking in thermal energy, where the energy is about, the energy that I'm kicking in is around nRT, right? So I'm feeding in heat from my bath. This is at isothermal conditions. Right? So I could put it in a bath, for instance, if you want. This is a bath, constant temperature bath. Right. So that bath is either pulling energy out or feeding in energy into the gas. Imagine the bath is hot and the gas is cold. So it's feeding in heat into the gas. And what does Pivner tells us? Well, it says that for all the nRT that I kick in there, it's equal to this value PV. What is PV? Well, we know that the units over here is joules. Joules per Kelvin per mole times mole. Joules per Kelvin times temperature Kelvin. This is joules. So PV is also joules. It also has units of energy. Right? And this energy, right, what does it have to do with? Well, it has to do with pressure and volume. We'll look at this more carefully next week. But the idea here is that this is work. Right? This is pressure. This is the pressure of the gas pressing against the walls or the piston. So this is heat energy being input into an ideal gas. And what does the gas do? It compensates by that input of energy by pressing against the piston. Right? So I push in heat, and what does the gas do? The gas pressure rises, right? And then the gas starts to press against the walls more aggressively, right? And it presses against that piston, and that piston is allowed to move in this direction, right? So we change dV, right, as pressure increases, right? So the pressure of this gas as heat increases, dP is greater than 0, so the pressure is increasing, right, in conjunction with nRT, and the result is to equal is that the volume also increases, right? So the heat comes in, the pressure increases, it applies more of a force, it pushes the piston open. Right? And so all this is just an energy conservation equation, right? It says that for an ideal gas, that the heat in is equal to the work out. That's all Pivnert is. It says that for every unit of thermal energy you put in, you get an equal amount of pressure volume, which is just increasing the pressure of the gas and pushing against the walls. Right? So that's all an ideal gas can do, is just push. Right? So that's all Pivnert is. It's just an equality of two energies. What happens though, let's start thinking about this a little bit for Thursday. I'm done after this one sentence. If this isn't the only thing the gas can do, what if there are other things that gas can do other than just push? Right, so we'll think about that next class, that maybe we need to correct this because a gas can do something other than push against the walls of a piston. It can attract to itself, for instance. Right, so we're going to have to adjust this equation, and that's where Pivnert's going to break. Right, so we'll start breaking Pivnert next class. Have a good day, guys. Thank you.